Welcome to Easy Math TV. Here we have a video discussing probability, and I think the best way to learn probability is just to look at examples and think through them and try to understand what the thinking is. So I've got 11 exercises here that we're going to just do and work through. So basically, I just want you to understand what the thought process is and how do you interpret the information that's given to you, and then what do you do with it. So, so I've come up with a kind of a selection of exercises here that kind of cover some of the basic principles of probability. And we're not going to get like into too deep with probability, but just so that we can understand some of the basic concepts. So let's read the question and then talk about how we would answer it. The first question, let event A denote an event where you're placing a dollar straight bet on a certain lottery and winning. So basically, event A is placing a bet and winning. The winning part is going to turn out to be the important piece here. And then it says, suppose that for this particular lottery, there are 3,780 different ways that you can select the 4 digits in this lottery with repetition allowed. So it turns out that detail was not really necessary. All we need to know is that our sample space, all the outcomes, is 3,780. So there just happen to be that many different outcomes that could occur, or like numbers on the ticket. Only one of those 4-digit numbers is going to be the winner. So the first question is, what is the value of the probability of A, the probability of winning? So we need to look at this in terms of how many outcomes there are that involve winning, and then divide by the total number of outcomes. That's pretty much it. So it has nothing to do with the dollar that you're betting. It has nothing to do with like how much you're betting. It's literally just how many ways are there of winning divided by the total number of possible outcomes. And so basically what we're going to be doing is we're going to take that number 1 and divide by 3,780. And that's going to give us our answer. You literally just have one chance out of 3,780 of winning. So you can either express that answer as a fraction, or you can do the calculation, just do it as a division problem on a calculator. So you can basically go bring up a calculator and calculate 1 divided by 3,780. And I'm not going to show you this every single time, but basically probabilities are generally, you're dividing two numbers. And so that's equal to 0.0002645. And I'm not rounding it at all, unless it tells me to. So that's the probability of winning. And you can see that that's a very small number. The more zeros you have after the decimal point, the closer to actual zero this value is. The second part of the question says, what is the value of the probability of A complement? So that's the symbol for A complement. So basically the probability of losing. The opposite of winning is losing. So what is the probability of losing this lottery? Well, we know that the probability of the complement is 1 minus the probability of the event itself. So we just take that answer that we just got and subtract 1 from it, and we get 0.99973,545, which is what we would call in statistics a near certainty. That is a near certainty because of the number of nines after the decimal point there. 0.99973,545 is what we call a near certainty. So that's question number 1. Let's go to question number 2. This is a little more involved, so we're going to need to understand what's going on in it. It asks, it gives us this information. A school administrator was supposed to use randomness to assign order in which student candidates' names appeared first on voting ballots for student government. So you're putting names on ballots, and there's always an advantage to the person whose name appears first. And that choice is supposed to be not alphabetical order. It's supposed to be based on a random selection or a random process. And so apparently someone was questioning, is it truly a random process at this school? So the names of children whose parents' income is more than $100,000 a year were placed on the first line of the ballot 37 times out of 45 randomly selected ballots. So they went back over previous elections and everything, and they just randomly selected 45 ballots. And it turned out that 37 times out of those 45, the first candidate happened to be the child of someone with high income. And apparently, so here's the important piece. The probability of a result that high is 0.0009425. So that's the important piece right there. Again, we have a probability that's extremely low, right? So assuming randomness was used, is the result the result that we got from our sample, the result of 37 kids from wealthy families being placed on the first line, is that significantly low? Is it significantly high? Or neither? So the first step of answering that question is to look at that probability of getting that result. The probability of getting that result was, in fact, a number that is, would you say that that was less than or equal to, or was it greater than or approximately equal to 0.05? So that's kind of our threshold for something that is considered to be rare. And when you compare those two decimal values, you say that that 0.00099425 is significantly less than or equal to 0.05. So our choice there would be less than or equal to. Then the next part of the statement says that so our result, which was 37 out of 45, is it much higher than what was expected, much lower than what was expected, or similar to what was expected? So considering the low probability and the fact that the in the directions itself, you notice that the statement that I pointed out to you, it says the probability of a result that high. So there's an acknowledgement there that the result was in fact high, or what was potentially high. So if the probability of that occurring was small enough, then it is considered to be much higher than what is expected with randomness. So then our conclusion is the last statement. The result of 37 is it significantly low? Is it significantly high? Or is it neither significantly low nor significantly high? So I think it's pretty obvious now what we're going to say there, that the result of 37 is statistically significantly high. So that's it's for our purposes for this class. I'm more interested in whether you can interpret a result rather than it's actually more important that you can interpret a result than the actual calculation itself, even though we're going to go through some examples of that too. So let's do a few fill in the blanks so that we can make sure that we understand our vocabulary. The first fill in the blank. The blank for a procedure consists of all possible simple events or all outcomes that cannot be broken down further into simpler events. And I even have some possible terms that could go there. And the answer to that is sample space. That is the sample space. It is all possible simple events or all outcomes that cannot be broken down further into simpler events. That's our sample space. Question number 4. Fill in the blank. The classical approach to probability requires that all possible outcomes are what? So this is just concerning, what is the classical approach to probability? Do you understand what the definition of that is? And the definition of a classical approach to probability assumes that all events are, or all outcomes are equally likely. Okay, equally likely. So, because often we don't know what the probabilities of things are. So when you don't know what the probability of an outcome is, we're usually dealing with things where something either is or it isn't, or something is positive or something is negative. So, whenever you have opposites like that, and you don't know what their probabilities are, you have to assume at the outset that they are equally likely until you have a reason to believe otherwise. Let's do one more fill in the blank here. As an experiment or observation is repeated, so if you repeat something again and again, then we calculate the relative frequency of any single outcome. Okay, so you repeat an experiment or an observation, you write down its relative frequency, and then you just keep doing that, and you write down all of the relative frequencies and maybe come up with an average of that. But the relative frequency of any single outcome begins to approach the actual or theoretical probability. This principle is known as the law of large numbers. So the law of large numbers states that the more often you repeat an experiment or observation and calculate a relative frequency, the relative frequency of an outcome is going to begin to approach the actual probability of that occurring. Another vocabulary question here, number 6. One of these represents the odds in favor of an event A occurring. The other represents the odds against event A occurring. Which is which? So I want you to notice the difference here. The first one is that you are dividing the probability of A on the top divided by the probability of its complement. So that represents odds in favor of an event occurring. If you do the opposite, if you take the probability of the complement or probability of not A occurring and divide by the probability of A, then you get the odds against A occurring. So the order that you divide the numbers in determines whether you're getting the odds in favor versus, as opposed to the odds against something happening. Question number 7. Suppose there are 15,958,866 adults in a certain region. So that's a large number of adults. That's like almost 16 million. You can round that to 16 million. If a polling organization just randomly selects 1,235 adults without replacement, are those selections considered to be independent or dependent? So this is about independent events, or are two things independent or two things dependent? And so we have a kind of a twofold part of our answer here. The first is, regardless of the size, like even though the population is huge, the selections are dependent because the selection is done without replacement. So by definition, that selection was done, and the results are going to be, for each observation, will be dependent observations. However, so there's a however here. can the selection be treated as independent for the purposes of calculations? And the answer to that is yes, because the sample size is less than 5% of the population. So what you would do there is you would divide 1,235 by the 15 million. 1, 2, 3, 5. So, is your sample size significantly smaller than the overall population that you are studying? 958,866, correct? 15,958,866. So I'm just dividing now, and we get a very, very small decimal. So 5% would be 0.05 here. So this is much smaller than that, which means that like the actual impact of the second adult on the first adult, if it's a random selection, is is so minimal that it's basically zero. I'm going to continue these examples in a follow-up video. So this is just video number 1. In video number 2, we're going to do some calculations with probabilities, and we're going to do some conditional probability. All right. So like, subscribe, comment down below if you're enjoying these videos, if you find them useful, and I'll see you in the next video for question number 8.